So we'll start the next session now. Wonderful. So I'd like to introduce Ed Rooth, who's going to be giving an introduction to Google's infrastructure for everyone else. Thank you.
Hi, how's everybody doing today? So? CoreOS Fest? Yeah? Okay. So my name is Ed Rooth. I work at CoreOS. I was one of the early employees at CoreOS. I've been there from the beginning, so I've seen a lot of the systems evolve and the things that we've been building over time. And I kind of head up the Tectonic team now. And just a little bit of an agenda for today. Like what I'd like to cover is, the slide's not moving. There we go. Okay. So I just want to cover a little bit, just talk about what Giphy is and what Tectonic is. These terms that you may have heard a little bit around here and from CoreOS. Why we decided to start building this sort of infrastructure and how we're actually building it and how you can kind of get started using these sort of things and this type of infrastructure with your projects. So before I get into all the definitions of things, I just want to kind of go back a little bit and explain like how these systems kind of evolved, right? So it all started with just running a simple server, running a website, whatever it is. Then eventually systems get more complex, you need more servers, databases, things like that. And then eventually we had virtual machines, so we had virtual machines on the servers. And then we started building APIs around these VMs, which is the cloud. So it means we had more and more servers to manage. So there's too many servers. The cloud made building servers really easy. Moore's law is still a thing. Hardware is really cheap. Just lots and lots of servers everywhere. And then, now you're starting to see companies have to manage all these servers, so it becomes a difficult problem just to manage these servers. So you have more servers, more problems. So some of the problems, patching the servers can be really difficult, especially when you have like 1,000 nodes. Like how do you go and issue a patch? How do you manage the dependencies on each machine to make sure they have everything that you need to run all the services? How do you manage access to all these machines? If you have 1,000 machines, if an employee leaves a company, how do you revoke their access, for example? Managing workloads as well, and application lifecycle management. How do you know which machines get what jobs and what services? And then even just identifying any sort of security issues across the servers can be challenging. So if you kind of just take the old school approach to having more servers, and as you increase the servers, you increase sysadmins because it requires a lot of manual work, manual intervention for a person to manage these servers. So what you would see if you just grew your server count, you'd have sysadmins growing right alongside with the servers in this like linear fashion, which we want to avoid. So what we'd like to see is something a little bit more like this, where fewer sysadmins can manage more servers. And Google already had this problem a lot earlier than a lot of us did, and other hyperscale companies like Twitter and Facebook. So they started solving some of these issues. And Google especially, they solved a lot of these issues internally. And they published some really great papers about these things, which inspired a lot of the work that you see happening in this emerging technology now. So we also started building it with Google and other community members. And we're building kind of like the open source version of what Google has already done internally. So that brings us to Giphy. So who here knows what Giphy is? No? So it's not a animated image format. It's what we call Google's infrastructure for everyone else. So this is a term that our CEO, Alex Polovy, coined just because I think he got tired of saying Google's infrastructure for everyone else so many times. So we just call it Giphy now. One thing that Google did when they took a new approach to infrastructure is there's a really good quote here which says, they fundamentally, it's what happens when you ask a software engineer to design an operations function. Meaning, they stopped thinking of servers as these things that require manual intervention and sysadmins to constantly hold the hand and maintain, but instead thought of it more of a software problem. How can we write software to maintain these systems? And there's a lot of interesting insight on this topic in the book they wrote, the SRE book, which I encourage people to check out if you're interested in this sort of thing. So I'd like to talk a little bit about Giphy and sort of some attributes of Giphy, like what would make a system sort of like this system that we need in order to run infrastructure this way. So I'm sure people here have heard the analogy of the pets versus cattle analogy. So first of all, servers are not your pets. Servers are, I think of them as a new CPU core. They're just sort of units of compute that are there to run jobs. They're no longer the things that you interact with directly. Instead, you interact with clusters. So clusters are like the new server. So pets versus cattle. The pets have evolved into cattle. And just, clusters, very simply, they're just multiple computers, multiple servers that you manage together as a single unit. And in the server world, you have like a single process on a single machine. You still have these single processes running in clusters across various machines, but they might be distributed out across multiple machines in your app in sort of like a microservices-like architecture. So how does this look internally at Google is they kind of have their own stack of various services. There's just a few of the major ones here, but down at the low level, they have their own operating system, which they kind of forked from Linux. They maintain some patches on it. For distributed kind of consensus and making decisions, they use Chubby, which is sort of analogous to etcd. And they have a sort of like a cluster operating system, which is called Borg, which is used to manage the clusters, and a monitoring tool that manages that called BorgMon, and an RPC framework called Stubby for remote procedure calls. And then they have some various authorization systems they haven't talked about too much in public, so can't really say much about that. But in the open source world, and at least CoreOS's view of these things, we also have analogous systems that you can use that would enable you to run a Google-like infrastructure. So from CoreOS Linux at the bottom to etcd, Kubernetes, we do a lot of work on this upstream, but this was actually initially started by Google about a year ago. Prometheus, another great monitoring tool, which is analogous to BorgMon. And then Google also open sourced gRPC, which is their sort of open source version of Stubby. And then for our authentication framework, we have an open source tool we created called Dex. So if you put all these pieces together, we kind of look at this as sort of like the full stack. So we distribute this product called Tectonic, which is what I like to call like the cluster operating system, which is all these components together, and Tectonic is our kind of commercial offering for the enterprise. So what do you need in an operating system for clusters? You need to have orchestration. You need to orchestrate basically the different resource utilization of the machines, scheduling the work, managing the state, what's the desired state of the system, what's the actual state of the system. And in this world, because it's software, it's more reactive. So we have not human beings, but software actually managing the servers and software managing the workloads. And in this sort of system, it's more like declare what you want, and the system will make it so. It's not necessarily spell everything out every step of the way. So here's kind of like what the architecture looks like a little bit. Up on top, you've got Etsy, the etcd logo representing etcd. So you've got your storage up there and your consensus. You've got an API server and a scheduler. The three boxes indicate like 3 nodes as like a control layer. And then worker machines below that communicate with the controller. So people and other systems will interact with the system via the API, and the scheduler decides where the work needs to go by sending it out to the different machines. The other thing that's interesting to note is that you can run this at a smaller scale. You don't have to have 1,000 machines in order to start running your infrastructure this way. So you could have just the API server and scheduler on a separate machine and just a single worker. And you could even just condense all of this down into a single machine if you want to start just developing or trying this out, or just building something so that you'll be ready to scale in the future. So a key component of the system, as I mentioned, is Kubernetes. Kubernetes is a significant component of the cluster OS. I kind of like to think of it as, or it's been referred to as the kernel of distributed like cluster operating systems. It very much fits in with our vision of where we see this type of infrastructure going in the future. And it was started by Google with, they've had over 10 years of experience running Borg, so they've actually put this into production with thousands and thousands of servers. We've seen it work in real life. They've addressed a lot of the issues. So we know this is built by people that actually know what they're doing. Some other attributes of a system like this that are required is just centralized administration and orchestration. You need to be able to access, like if you can't SSH into every single machine, you can't SSH into every single machine if you have like 1,000 nodes. It's just not practical. So you need some way to like have a centralized way to access these machines. So like in the previous diagram, you've kind of got this API layer that you communicate with. And SSHing into the machines is not really practical, and even with like config management tools and things like that, like under the covers, like essentially what they're doing is they're just SSHing into the machines and running commands. So kind of the old way of interacting with the server would be to say how to do something, where you might copy a file over and then start a process on the machine. So I'd like to think that in this new infrastructure, you don't say how, but instead you say what. So how many people here are familiar with Kubernetes or have used it? A few? Okay, so most people know kubectl. If you don't, this is a client command line utility that you can use to interact with Kubernetes. So I can say kubectl run my app, and I give it the container image I want to run, and I give it how many replicas I want it to run, how many instances. And then down below on the bottom, I say kubectl get pods, which list out the running pods in the system. So I can just say, I want you to run my app, run one of them, and it just makes it happen. I didn't say how to do it. I didn't say this is how you do a pull. This is how which machine to run it on. The system just figures it out. So then I can say what again? I can increase the replica count to 4, and then down below you see I'll have four pods running. And if I want to go back down to 1, I can say what one more time, which reminds me of a movie I saw once. This is just sort of a visual representation of the previous slide. So you can see how there's a component in Kubernetes called a replication controller that sits next to your pods, and it makes sure that it controls the pods to make sure that the desired count are running. And another thing I want to just kind of call out is, automated systems are not the same as automatic systems. Of course, we want automation, but I think of an automated system as something that is kind of documented in code, like run a series of scripts, do a series of steps. But if you encounter some kind of error along the way, you might get into a weird state, and being able to like roll back or adjust or react to that issue is not necessarily always present in an automated system. So automatic systems kind of have this concept of failure built in, this concept of being like a living, breathing system that knows how to react to unexpected events. So in this Giphy world, dependencies have to be isolated for every app. Your apps, we're going to have to migrate through the cluster to different machines. These are, of course, containers. Apps, ideally, are developed in a sort of like a way that follows a 12-factor sort of best practices, where you have your configuration and your secrets and things separate from the actual code that's running in the cluster. And just having a consistent API to deploy things against makes managing this stuff a lot easier. And you can also do things like have canary builds and rolling updates, which, for example, if you had a server or a service that you're running in your cluster that's load balanced, so say you have an app that's at version 1 and you've got 4 different versions of it running, and all the traffic is coming into the load balancer. Say you want to deploy version 2 of this app, but you're not really sure if it's production ready or if it's going to fail or if it's going to introduce a regression. You can introduce that version 2 into the cluster, and then you can connect it up to that load balancer. And then you can start monitoring it and see if it's behaving as expected or causing any issues. And if it turns out that it's okay, then you go ahead and slowly roll that out and do a rolling update. And the system makes this sort of thing a lot easier to do. Another attribute of the system is being able to have mixed workloads. In the old sort of servo model, you had like, different environments for staging and production and dev and things like this. But in this sort of model, you could ideally run mixed workloads in the same cluster. And in order to do that, you need to have some kind of logical partitions of where things are running. So at least in the Kubernetes model, these things are namespaces, and every sort of job and service gets launched into a namespace, and then you define your authorization access across the different namespaces, who can access what. And we want to build these systems to be trusted and secure from the bottom up, ideally from the firmware layer to the OS, the container runtime, and the cluster OS itself. And ideally, only trusted code is executed. We also expect every single human, machine, process to be authenticated and authorized, and all the communication between all the different pieces of the system to be encrypted. And as I mentioned, it's an automatic system. It is dynamic, so failure is expected. And this could happen either at the individual service layer or individual machines. Maybe there's a hardware issue. The storage layer being etcd, like you could lose a node, and because it's distributed, it's okay. You could, when the node comes back online, it'll resync with the cluster. And you could even take this up to the cluster level and even entire regions. So maybe you have like multiple clusters running, and you could even withstand an entire cluster outage if you had a multi-cluster deployment. Another important aspect is just logging and monitoring and alerting. Because you're running so many processes across so many machines, you need a way to have insight into the system. Otherwise, you're just kind of flying blind without any idea of what's going on. So Google's actual infrastructure and this idea of Giphy and the stuff that we're doing at CoreOS and the open source tools, like what's actually different between those. So in the open source things, we actually want to have more compatibility with existing tools and projects like Docker and Calico and Prometheus and things that are just kind of off the shelf, already exist in the open source world. And it also incorporates lessons that have been learned from Google at Borg, so while running Borg. So Kubernetes is actually not just a clone of Borg, but it's the next iteration of Borg. So they've taken a lot of lessons that they learned during Borg and started incorporating those into Kubernetes. And why even bother doing any of this? Because we want to build for scale. You want to spend time managing your apps, not your infrastructure, and you want to have highly available apps if possible. And I think this requires like a little bit of a different way of doing development, having like a new paradigm for how you develop your systems and run your infrastructure and how you develop your applications. And another thing is, since security is such a crucial component to this system, at CoreOS we believe that if people start running their systems and their infrastructure using these Giphy-like models, then the internet overall would become more secure because more and more people start adopting this and these systems are more secure. Eventually the internet will become more secure, which is one of our kind of core missions at CoreOS, is to help secure the internet. So along the way, like we started out on this journey to Giphy, we started with a few different things. We didn't want to start from scratch. We leveraged existing protocols and standards and work that's been done before. So for example, the Raft consensus protocol is used in etcd. The Omaha protocol is the same protocol used to update Google Chrome and the Chrome OS. We use that same protocol for updating CoreOS Linux. And OpenID Connect, which is kind of an extension of OAuth 2, is used in our DEX authentication system. So when we started working on this stuff, we wanted to start from the bottom up. So we started with the operating system itself. We wanted a minimal server OS that could do automatic updates so you wouldn't have to worry about patching your servers. I'm sure a lot of you are familiar with this from our websiters running CoreOS. But in order to do this, and maybe you saw Brandon's talk earlier about etcd, you kind of, to run an operating system this way that's going to be rebooting itself, you need a consensus system, you need containers, you need cluster computing, because you don't want your workloads to go down as your servers go down. So part of this is containerizing all the things. I'm sure a lot of people have experience with containers, but just containerizing your apps is kind of the first step. It's not, the final step. Because just like the servers, if we have more containers, we also have more problems. So we're solving one set of problems and trading them for another set of problems. So we dog food a lot of stuff internally at CoreOS, and we also experience these issues and hear things from our customers and users. So one of the problems that we encounter is once you start having all these container images, where do you store them all? So you need some kind of image registry, and you could just store them in the cloud somewhere, but a lot of customers want to have control over that, and they want a secure place to store them, which is why we teamed up with the Quay team, and we offer Quay hosted at Quay.io, and also Quay Enterprise Registry, which you can run locally within your own infrastructure. Another problem that we encountered was with some of the decisions made with the Docker model. We wrote a little blog post about this a while ago. I don't know if you guys saw that, but basically just the coupling of the components and the lack of assigning of the images and things was not really how we sort of saw the evolution of this infrastructure going. So we came up with AppC and Rocket. So AppC is a container specification, and Rocket is our implementation of that specification. So sort of the issue with Docker was Docker runs in a daemon mode, so it kind of sidesteps the init system, meaning you lose a lot of the primitives of the init system when you run everything in the Docker model. And having the Docker daemon alongside another sort of cluster OS kind of doesn't make sense. It's more moving parts that you have to think about and manage. So we prefer the Rocket model where it's just a standard Unix process. And just a side note, I'm sure you've seen this sort of image before about the analogy of the standard shipping container. So this is actually an example of an implementation, not a standard. So the standard for this thing would be the ISO 668 spec. So this is the spec that tells you the exact dimensions of how to build one of these containers. So this is analogous to AppC and Rocket, where AppC is the spec, Rocket is the implementation. So another issue that we came across was just building a lot of apps and customers building apps too. You need some sort of user authentication system for every one of the apps you're building. And we're reinventing this same solution, the same problem every single time. And we wanted to have something that was a little bit more of a common solution. So we came up with Dex, which is our open source identity store. It's basically an authentication provider that federates to other authentication systems, or can work as a standalone system, which leverages OpenID Connect and OAuth 2. Another problem is a lot of times when you're going through these examples of how to build containers, usually the first step is like import all of Ubuntu or import all of Fedora, and you end up with these really giant containers that are like 500 megs. So there are already some good tools out there for dealing with this stuff. So we use Go for a lot of our development, and Go has a really nice feature where you can just compile everything down to a static binary, so it pulls in all the dependencies for you. So then your container then actually just ends up being a static Go binary wrapped in a container that's just empty. So most of our Go apps end up being in containers that are about 30 to 40 megabytes in size. Build root is something that's already existed out there. My colleague Brian Redbeard gave a talk on this a while back at one of our meetups. And it's basically a tool that you can use for building minimal Linux images. It's made for running things on embedded systems like routers. But you can actually use this to build ACI images and Docker images too. And then we also developed AC Build, which is a tool for building ACI images. So don't make Brian Redbeard mad, because if he sees large containers, he gets angry. And there's the link to his slides from the talk that he gave. It's really, really interesting stuff. I encourage you to check it out if you're interested in building smaller containers. So there's a whole other set of problems with running systems like this. So sometimes you might want to have co-located processes running on the same machine due to latency issues. You might want to have a more intelligent scheduling system that's like affinity-based scheduling or based on server resources. Port management is kind of a nightmare when you're running a lot of services on different servers and they're all trying to bind to the same port, for example. So there's a lot of these problems are solved by Kubernetes, which is why we feel so strongly about Kubernetes and why we're backing this project. But another issue that comes out of working with Kubernetes is the networking model, where every single pod in the system gets its own IP address. This is how they solve the port issues. And there's also an issue of having different software-defined networking layers and being able to plug in different ones depending on what you want. So this is where we introduce Flannel. Flannel is our software-defined networking layer. And this enables you to run complex systems with complex networking needs like Kubernetes across different environments. And CNI is our sort of open standard that we helped to create to allow like a networking interface like plugin for systems like Kubernetes to use, where they can delegate that the work of that off to a different system. And then, like I mentioned, you're flying blind if you don't have metrics or monitoring and alerting. So this is why we're investing in Prometheus. It's a great open source tool that came out of SoundCloud that already has a lot of great Kubernetes support. And then another thing, so if we're automatically updating the OS, like we're going to get to all the patches on the host machines, that's fine. But what about the vulnerabilities inside your containers, inside the dependencies that you've put inside your containers? You have no insight into those. So this is where the Claire stuff came in. It's another open source project. Brandon talked about this during his keynote. And he also, I think, showed you probably the same screenshot with inspecting some of the images and seeing the vulnerabilities that are available. And then just in general, visualizing and configuring your cluster. In the Tectonic stack, we have a tool called Tectonic Console, which, as in the other slides, I showed the replication controllers and the pods and things spinning up and labeling these things and accessing them in the system. This is our sort of UI for interacting with those bits. And then another thing you don't really hear about too much with the cloud stuff is running this on bare metal. A lot of customers also have their own data centers. They want to run things on hardware. The cloud's great because they have all these well-defined APIs around everything, but when you get to bare metal, it's a different story. So we have a few different components that we built. Both of these are actually open source. Ignition's sort of like our early stage provisioning tool for booting. Not just bare metal servers, but it helps a lot with the bare metal case. And CoreOS bare metal is another open source repository we have that has some tooling in there to generate ignition configs for your machines. So like if you're in a network booting environment using Pixie or iPixie, you can get machine-specific ignition configs based on those machine attributes. And then trusting bare metal, we have a solution called distributed trusted computing. Matthew Garrett's going to be giving a talk on this tomorrow, and definitely check that out. We're kind of pioneering this sort of level of security and securing hardware in the data center. So again, if Kubernetes is the kernel, I think of Tectonic as the cluster OS. It's kind of like the distribution of Kubernetes. We like to think of it as off-the-shelf Giphy. It has all these components together so you can run your infrastructure like Google. And just to highlight again, Kubernetes is a crucial component of this, which is why CoreOS is investing a lot of our resources into upstream Kubernetes. Even in Tectonic, we don't fork Kubernetes, we don't maintain separate branches or patches. We contribute everything upstream, and when we ship Tectonic, we ship vanilla Kubernetes. So we have, we've already contributed the OpenID Connect authentication hooks into Kubernetes. We're working on authorization systems now upstream. The ability to have the worker nodes come online and automatically connect to the server and generate their TLS assets. The idea of having the container runtime in Kubernetes itself be configurable, so you can choose either Docker or Rocket. So it's a project we're calling Rocket Netties. And we have a team that's focused on purely just performance in the cluster. So our team at CoreOS, we wrote a blog post about this. They doubled the performance of the scheduler in Kubernetes. And this is all stuff that's already, not all of this, but that part of it's already shipped in upstream master. Brandon gave a talk on etcd3. We're working with the Kubernetes team to get all the cool new etcd features and performance improvements into upstream. And we also have another open source repository called CoreOS Kubernetes, which is one of the more popular places to go if you want to launch a Kubernetes cluster easily. especially with support for AWS. And then the last thing is actually like a really significant thing that we're working on, which is improving how the bootstrapping and the upgrading of Kubernetes is actually done. So we're spending a lot of time simplifying that and making it so that you can run Kubernetes on top of Kubernetes itself, so that you can do things like upgrade the cluster in place. And for the future of all this stuff, we're going to continue to build more management tools. We're going to extend platform support to various other providers, cloud providers. We want to extend Prometheus support and its capabilities. And then another sort of topic that's really interesting upstream is the idea of federated clusters. You may have heard of it called as like Kubernetes. The idea that you could have sort of a higher order cluster that manages other clusters, which would enable you to do like mirroring of one cluster to another, or having like clusters running in different regions of the world and having a central point to administer them. So just a summary of some of the things we discussed and some of the things that we believe in is that I think for this to be adopted widely, open source is key. Like this stuff has to be open source and has to work with existing tools. Security is key. Without this stuff being secure, it's not going to work. And without updates and automatic updates, you're not going to achieve security. And containers, as we saw, they're a crucial component, but it's not the end of the story. And I would just encourage everybody to sort of start thinking about this way of developing and deploying their infrastructure, because even if you're not running 1,000 servers today, you can at least start building your applications and structuring your infrastructure so that when the time comes that you need to scale, it could be just as simple as plugging in more machines and everything will just scale out automatically. So that's all I have, and I'm happy to answer any questions. Yes?
You mentioned storage in one slide.
Yeah.
Still looking for the solution for running persistent storage on Kubernetes or any other modern cluster operating system.
Right. Yeah, that's a common question, and we're still working on that. So I don't have an answer for you today, but we're looking into it, and we know it's an issue and know it needs to be solved. It's just we're quite busy doing a lot of other things at the moment, building etcd and then CoreOS Linux and Tectonic. So we're going to address that at some point soon, but I don't have an answer for you today. I'm sorry. Any other questions? Yes?
You mentioned the automatic TLS configuration of workers.
Yes.
So that you give some more details, like what's this going to look like? How it's supposed to work?
Yeah, it's a good question. So the question was about automatic TLS generation for the worker nodes. So this is actually going on now. A proposal was just submitted and merged into Master of Kubernetes about this. And it's probably a bit too much to cover right now, but I'll be doing office hours at the booth from 1:30 to 2:30. We can discuss a little bit more or after this. But the basic idea is that just when the machines come online, they generate a certificate, like a CSR, and the key, and they submit that to the API server. And then that just gets kind of held in a queue to where a user can then come in and say, like, I approve this or I don't approve this machine. Yes?
So in the world of containers where you isolate the components that can be separate deployed at any time and scale, which is a problem to having those components running in different environments with different configuration sets for these environment variables, as per 12 factor and otherwise.
Right.
What is your recommended solution to the problem how to manage secrets, like the environment variables or some certificate files that applications need, components need? What would you suggest? What are you working with?
Yeah, so I think the question was, when you're deploying your containers and you need to do configuration, like mount in different configuration for different environments and secrets, what's the recommended approach for secrets? So in Kubernetes itself has the concept of two concepts. One is called a config map and one is called a secrets. So the recommended approach today is to load all the secrets into a secrets object in Kubernetes. And then when you're running your container, you can reference that secrets object and mount it in as a volume. And then you can inject those secrets into your pod or your container definition through environment variables or configuration flags. Okay, I think that's all the time I have. And again, I'll be at the booth from 1:30 to 2:30, so I'm happy to chat with anybody if you want to come by at that time. Thanks.